Okay, thank you very much for that introduction, and I'm really quite honored to be here and speak to all of you. I prepared this talk keeping in mind that I think we're at a very special time now in cognitive science, where we're beginning to see synergies that we only saw in isolated places previously. And so what I wanted to do today was talk about computational models of creativity, but also to think about how these computational models are also having an impact on us and on human cognition, where I think we've seen it go the other way. We often use human cognition as the inspiration for computational models. I think we're seeing it go back and forth now, and that's what I want to try and communicate to you today. I think the concepts of curiosity, novelty, and surprise are some of the foundational concepts that have allowed this back and forth and this synergy. I also want to acknowledge and thank UNC Charlotte. I went there in 2012 after being at NSF for a while, and I just have to admit that it's one of the most open environments I've ever worked. If anyone's interested, we're always hiring. But it is a really great community, and I wanted to acknowledge that. I also wanted to acknowledge NSF. So I was there for 4 years, and I think those were 4 amazing years of learning from people like you by reading all those proposals and working with the government and Congress to think about what are the directions for science. And I also want to encourage you, if you're ever thinking, is this a good time for me to go to NSF, you should consider that. We need good people like you there. So let me get started. I thought I'd start with a sort of a research trajectory. It's my research trajectory, but it also reflects things that were happening over time from the 1980s until now. In the early work in the 80s and the 90s on using artificial intelligence, knowledge representation, and different ways of building computational models to think about creativity, to play around with the ideas of creativity, to use human cognition as that inspiration for building computational systems that were able to identify creative solutions, to think outside the box, to extend things a little bit. And on the left, you'll see this knowledge-based creativity. That's the idea of building knowledge-based systems that can reason about whatever design or problem they're programmed to reason about, but to be able to reason about them so that you get to innovative or novel solutions. It was hard work. Those of you who are building these systems, it was really hard work. Understanding human creativity was difficult enough, but then trying to build a computational system that could actually behave creatively was particularly challenging. And I think we learned a lot, not just about human cognition, but we also learned a lot about the areas in which these were being built, whether it was in the area of building design or mechanical systems design. Just that process helped us understand what it was. What is creativity? That second item there, which is machine learning, that was when I started thinking about curiosity as playing a major role in creativity. And this is a project and then ultimately a book that embedded curiosity into a reinforcement learner, a machine learner that focused on things that were a little bit outside their knowledge space as the basis for learning. And that was a really interesting project because it brought forth this idea of curiosity as being somewhat integral to creativity. Then I moved away from the AI part for a little while and focused on a different aspect of computing, which is human-computer interaction. And there we were beginning to see different modalities, different ways of interacting with computation that moved us off the keyboard, moved us into gestures and touch. And there we began to think that maybe these embodied interactions, this use of our body as we interact with digital information, would stimulate creativity in ways that using the keyboard and looking at a screen did not. And so that was a transition from AI into HCI, all in the focus of how does this enhance human creativity? How does this help us understand human creativity? And now we come to this third period, which is this idea of creativity in humans being inspired by computation. So if you look at that top row from AI to HCI, now we're beginning to see research and, in fact, actual development implementation of things called human-centered AI. We're beginning to see in our research a shift from simulating creativity by building computational systems that are creative into stimulating creativity, where we're seeing computational systems that can stimulate human curiosity and human creativity in ways that they couldn't do before. And so on that right-hand side, you'll see I'll be looking at deep learning as sort of a sandbox or a playground for moving around spaces, and as the basis for inspiring creativity in humans. So here we are. What is the role of computation in creative systems? And I mean creative systems in the broadest possible sense. Humans and machines. And we see at the top two that we've become quite comfortable with. We see HCI researchers are building tools that support human creativity. And the second one, we've even become somewhat comfortable with AI researchers building algorithms that generate creative artifacts. This has been going on for decades, and many of us think of this as that's what we mean by computational creativity. But what I want to talk about is that last one. It's labeled co-creativity here, and the idea is that there's an HCI component, certainly, and an AI component, but the idea is to build systems that support co-creation, where the computational system is contributing to the creativity and the human is contributing to the creativity. And there's a kind of synergy there that we haven't seen before. And what we're beginning to explore then is what is that interaction between cognitive and computational creativity. And as I hinted before, I think curiosity is an integral part of that. I think curiosity is, in fact, a precursor to creativity. If you think about curiosity in its simplest definition as the desire to know or learn, then curiosity is that desire or that arousal to think of something that we don't know already, to look around, to understand something that we haven't looked at before. In the early work on curiosity with Berlin, he defined curiosity as a trait or a state. I think this is an interesting conversation, discussion. We could even possibly say that creativity could be considered as a trait or a state. A trait being, of course, that it's something that's inherent in us. This person is more curious than that person, or this person is more creative than that person. And it's a way of being in the world. It's embedded in the way we see and interact with the world. It's our trait. Or it could be a state. So we could be in a state of curiosity or a state of creativity. I kind of like the idea of the state, because if you think about curiosity as a state, then we can move into that state of curiosity through some sort of stimulus or some sort of presentation of information that moves us from not being curious to being curious, which is pretty exciting if you think about computational creativity, that we can now design systems to intentionally make us more curious. I'll be talking about this in the context of design and creative design, but at the end, I want to challenge you to think about how this might, in fact, be a potential way for us to get out of our echo chambers and our information bubbles, to mitigate this concept of human bias that we're beginning to see run viral and rampant in social media. But first, let's go with creativity and design. Berlin had quite a lot to say about this, and I won't go into too much detail on it, but there are different kinds of curiosity estate: the epistemic, which is the desire for more knowledge, which is the kind of creativity stimulus I'll be talking about today. There's also that perceptual curiosity, which is sensory, and that goes back to that work on embodied interaction and being able to interact with information with more of our sensors than just our eyes. And computational systems play a significant role in that too. If we accept that curiosity, or even creativity, is a state, then now we can think about stimulating it. How can we develop systems, or co-creative systems, in fact, that stimulate this? And here you are, the one curve, which many of you may be familiar with, and I've got an illustration of it here. This isn't a true image of the one curve. But I thought it was important to think about this because we can start to build systems or computational models that traverse this one curve, that use it as a reference point. When we think about curiosity as trait, we might think about this one curve as providing a basis for characterizing different individuals may have their peak point for arousal at a different place along that horizontal line, which is this degree of stimulation. Some of us with very little stimulation are highly creative and highly curious. Some of us, the stimulation might be a little bit more to the right. But what this allows us to do is to think about that sweet spot for individuals, or for types of problems, or types of search spaces, and begin to think about where is that comfort zone when the stimulation is in fact engaging us in curiosity or creativity. I want to move on. I have a few background slides, and then I'll get to describing some of our work. But the cognitive models associated with creativity, the work on this has been ongoing also for decades, and all of it has become even more relevant today as we begin to think about how computational systems might stimulate curiosity or encourage creativity. We can think about the different kinds of creativity that have been identified. Bowden talks about combinatorial, exploratory, transformational, and she talks about transformational as being that one that is really special. That's when you're really moving outside into a completely different reformulation or formulation of the problem or the solution. And then the work by Jiro and myself in the Heron Island conferences, we talked about many kinds of cognitive models: analogy, emergence, coevolution, re-representation. All of these early models of human cognition that are associated with creativity now become something we can look at again in terms of how does the computational system stimulate these. Analogy making is a really important concept in creativity. If we can think about how we stimulate humans in the process of being creative or thinking, analogy is obviously an important concept. You give an example of something that's similar but different, it encourages analogy making. Re-representation was also a foundational concept that was developed over many years, that in order to enable analogies or enable new ideas, it's sometimes helpful to take the representation space and transform it into a different representation. And that leads me to this next slide. I'll be talking today about deep learning as a mechanism, as a computational process that allows us to build new spaces, new representation spaces, without all that hard work of the cognitive models being transformed into new spaces. With deep learning and deep neural nets, we have concepts like autoencoders and recurrent neural nets. The really interesting thing about the autoencoder is it takes as its input some representation, say of an image, and through its processes of backward propagation, it encodes it into a different representation space, which I'll call the latent space, commonly called the latent space. Then it decodes it back into its original representation. And that process of training the network creates this latent space, which is kind of cool, because now we have a space in which we can operate that is subsymbolic. It transforms what might be representational features, say in an image of stroke data or bitmap data, into a feature vector of numbers. When you have a feature vector of numbers that represents an image, well, because you can decode it, now you can play around in that space in ways that you couldn't play around if you were looking at only computation on stroke data or bitmap data. Recurrent neural nets do the same thing, or provide the same facility. They don't do the same thing, where you have an input pattern, and these are most typically classification networks, but any of those internal layers can then serve as a representation similar to the latent space. We've seen amazing things happen with this. We've seen this concept of style transfer. And style transfer, when you first see it, kind of looks like magic. It takes a source image like the scene on the left, and it takes a style of Van Gogh, and it transforms that source into the style of Van Gogh. And it's automated, and it's based on deep learning networks of style representation. And it's possible because it's moved it into this vector space. It's not dealing with the bitmap, it just decodes back into the bitmap, which is pretty exciting. I also want to refer to Schoen. I think his work was fairly important and influential in the area of design and creative design, in recognizing that the way designers design is heavily influenced by this ability to sketch, produce external representations, see those external representations and shift them into an internal representation, and then move around in that internal representation space that puts us in a different place in the external space. I like this diagram because it sort of matches what I've been doing with our creative sketching partner and with our use of deep learning networks, is that we take the external design representation created by the human, we map it into that latent space using deep learning networks, and we move around in that space, and then we bring it back. We decode it and bring it back into that external representation that the designer is using. And so it's kind of like Donald Schoen's idea, only with the assistance of computation. I have no idea how long I'm taking because the number is below the cut. So now I'll talk a little bit about a project that I've been working on for several years with faculty and students at UNC Charlotte. It's about co-creative design with the conceptual shift. Now, conceptual shifts, conceptual blending has been a topic of interest for researchers in cognition and computation for many years. And what we wanted to explore was, can that conceptual shift be modeled computationally with a deep learning network and presented back to the designer, which leads to their developing the conceptual blend. So we don't automate the blend, we automate the shift. And that's consistent with what I was talking about before, which is now we can have computation that intentionally encourages or stimulates curiosity and creativity. So the features of our system is we were focused on what is a conceptual shift in this area of design. We use deep learning models, so we have that latent space as our re-representation, our play area, our area to move around. And we defined a conceptual shift in this context as having a visual similarity component and a conceptual similarity component. So on the right, you'll see a sketching interface where the designer is given a design task. For example, design a street light for safety at night on a city street in a small town, where the left-hand top sketch is the human designer's sketch. The right-hand top sketch is the sketch that the computational system places on the canvas. And then in the bottom, in the middle, is the sketch that the designer makes after being stimulated by the sketch on the right. Now back to our cognitive models, what we wanted to explore was, depending on how similar, how novel the sketch stimulus is, would we see different levels of creativity? And we said combinatorial creativity is obviously a kind of creativity, but it's about putting two things together. It keeps you in a similar search space, where transformational is when you actually expand the search space and you find things that you didn't have in your space before. And we thought that maybe the novelty metric for the conceptual shift could be categorized as being high, intermediate, and low, that we would be able to see this diagonal happen, that the level of novelty would lead to different levels of creativity. So what was our model of conceptual shifts? We said, first of all, we used that deep learning networks, and we constructed both a visual and a semantic model of the sketches in the QuickDraw data set. So the QuickDraw data set is 50 million sketches that are represented as a sketch and a label. And so it might be a sketch of a bridge, or a sketch of a nose, or a sketch of a strawberry. And we use that data set to train up a neural network that used the stroke data and gave us that latent space for feature extraction. And then for concept similarity, we actually used a word embedding model that was already generated that used Wikipedia, and we used that to create a latent space for the labels associated with the sketches so that we could extract feature vectors. So our process looks something like this. We have the user's sketch that was put on the canvas in response to the design prompt. And that user's sketch was fed into the neural network, and we extracted the visual features based on the trained neural network. Oh, got it. Okay, then we located it in a sketch cluster, and we categorized a set of sketches from the database, from the image database, that were high, medium, and low similarity. Used those sketches to extract word-to-vec features on their labels, and then clustered them into high, medium, and low. I thought I would show you a little bit more detail. I won't dwell too much on this, but what it means is that there's a learning stage first. So you'll see at the second level of the top, all the images in the database were used to train up a neural network. These neural networks work well when there's a lot of data. So 50 million sketches was a really good data set for us. It gave us enough data to actually have a reasonably good latent space representation. Wikipedia has a lot of words in it, so that was also another good deep learning model. Deep learning models don't work well when there's not much data. And then we used the visual features as the first cut. It had to be somewhat visually similar, and then we rated those according to their conceptual similarity. So sometimes a bridge looks like a rainbow, for example. And so the person sketching a bridge, it might pull up a rainbow, and then we would see what is the conceptual similarity between a bridge and a rainbow. So we did a user study, and we had this hypothesis based on this graph on the right, that if it was very high similarity, or in the category of high similarity, remember, it's not identical, it's similar. So it's similar but different, more similar than different, that we would see more combinations. And if it was low similarity, then we'd see something very different, something more transformational. We used a Wizard of Oz study for this. The interaction model wasn't quite developed. The AI was all there, but in terms of where to put it on the screen and the response time was all done by a person. We actually studied this with architecture students because we wanted to have participants in the study who are very comfortable with both sketching and with designing. And the procedure was fairly standard. We trained them up, we had them perform a task, and then we did a retrospective protocol analysis. We used a very simple off-the-shelf tool called Sketch Together. The training session was 5 to 10 minutes, and then a 25-minute design session. We had 3 design tasks, so 3 conditions. And with each condition, it was always associated with a level of similarity, either high, medium, or low, and each person participated in each of the 3 conditions. We did some coding on the data that we collected. It was double-coded so that there were 2 different coders. They coded the results of the sketching session that the human did, whether it was combinatorial, exploratorial, and transformational. And just to give you a sense of how we did that, combinatorial was when 2 elements were brought together, 1 element from the original sketch and then 1 element from the sketch presented by the AI. Exploratorial was more about exploring parts of the design space that weren't in the original sketch, but the variables were. So it's sort of extending the values of the variables into a place they hadn't explored yet. And transformational is when something from the inspiring design was brought in that isn't normally associated with, say, a bridge or a light on a city street. Our data for the coding was after they performed the design sketch. We asked them to talk to us about what inspired you to draw that 3rd sketch, and why did you draw it this way, and did you see a relationship between your sketch and the system's response? And I'll show you some examples of the results, but when you see that red marking on the sketch, that's when the designer or the participant made a direct reference to that part of the sketch when they were talking about it. So here's an example, high similarity. This is the source sketch, or the design task was the design a bridge, and the target sketch was what the system brought back, and you'll see it brought back a fence in these examples. And what the designers did was they took portions of the fence and just put it in their designs, and it was a really good example of this combinatorial. But it was something that they hadn't thought of before. You know, when they had designed the bridge, they go, oh, I forgot to put a fence, or oh, that fence makes me think about how the bridge could be supported with these vertical struts. Intermediate, these were examples of where the source sketch was modified based on the target sketch not by changing it significantly, but by taking one of the variables, whether it was symmetry or scale, and changing it to a different value. And then low similarity, these are times when actually the sketch didn't matter at all. It was usually the concept that played a big role, where they thought about an airplane and they go, oh, I'm designing a chair, but I could give it wings like an airplane. Or they thought about, oh, the chairs on airplanes recline, and I don't have a reclining part of my chair. So they then brought the concepts in. All in all, it was pretty fascinating to observe what people did with these and their explanations, because first of all, the sketch produced by the AI was intentional in its conceptual shift. And the human was very intentional about how they used that in different ways, depending on the similarity along that scale. So then we thought beyond the Wizard of Oz study, and we've actually implemented this and collected, in this case, 50 participants doing a design task, where they could move the scale on the visual and the conceptual similarity and choose how much difference or novelty or similarity they wanted. And they could choose when they wanted to be inspired. And what you're seeing here is that bridge task again on the left, and then the sketch that was presented by the AI. You can see that the visual similarity isn't very high. We also found that when visual similarity dropped, the conceptual the concept or the label of the sketch was what influenced their design. So, what are some conclusions from this design tool study? First of all, we learned that deep learning models and the latent space that they produce are really fascinating in terms of playing with novelty in a creative design. It allows you to calculate novelty numerically in a space that carries the meaning of the original representation, but with cosine similarity and other ways of measuring distance, it gave you a distance space that was much more comprehensive than we could have had if we looked at bitmaps or stroke data. The other thing that was interesting is these large data sets of words and images are an interesting starting point for exploring the meaning of distance and latent spaces. Like, what does it mean if this image is far from that image? By presenting it back to our participants and thinking about how, when you present something back to a human with the intention to encourage curiosity or creativity, you're exploring some kind of meaning that emerges from that latent space rather than being encoded in that latent space. And that's interesting for us. And then finally, that stimulating curiosity, which we explored here in a design task, actually is an interesting idea if you extend it into things like recommender systems. How would you stimulate curiosity in recommender systems? We all know that recommender systems are judged or valued on whether the person actually follows through and purchases or selects whatever was recommended. But that's been taken to the extreme where they find they have the best performance if you get it as close as possible to what the person wants. But if you want to stimulate curiosity, you don't want to get it right where they want it. You want to extend them a little bit and encourage them to be curious without losing the click-through or the value of the person selecting. In learning, we've also explored this idea of stimulating curiosity in learning rather than the teacher or the instructor, the human teacher, prescribing sequences of learning materials. You could use this concept of curiosity and this latent space representation to stage the learning so that it connects always with what the person's interested in rather than what the teacher was interested in. And then finally, social media behavior. One of the things we're exploring more recently is in social media behavior, we're beginning to see that people are falling into these echo chambers. And how could we use this concept of curiosity to nudge them out of their echo chambers, keep them inside their comfort zone in the one curve, but still nudge them? So I'm going to give some examples of other systems that we've developed using this concept of curiosity that's taken us out of the design space, but kept us within that curiosity and creativity space. One is a system called QChef, and this is the Curious Sous Chef. And one of the ideas is, can we use curiosity to actually broaden a person's palate? can we get people to try different foods or think about unusual combinations of foods by having that preference model of the user and then having a surprise model. Using that surprise model to feed back into the design space to stimulate the user with different recipes. And this was kind of fun. We did a few Mechanical Turk studies, and we did some studies with humans in the lab to look at stimulating them with recipes that were a little unusual. Like, you don't normally think of bacon and butter in the same recipe. In fact, in the recipes database that we had, it was an unusual combination. And so you could encourage chocolate bacon cupcakes. And then we had the vodka and the pecans. You don't usually see them in the same recipe, but they appeared together in a pasta recipe. One thing we haven't done is we haven't been able to connect this back to nutritional things. The unusual ones tend not to be very nutritional. We also developed a system called Curious George. And Curious George is a recommender system that's built on top of the Amazon book data. So we used the Amazon data about books, again, to train up our neural nets. And we used a recommender system that used a traditional content-based filtering method to select 100 books that are close to what that person is interested in or searched for. And then we re-ranked them according to how surprising they are. And surprising was based on mutual information, the PMI measure, which looked at how likely was it that two topics appeared in the same book across the whole corpus. And we used that in a study where we found it didn't actually reduce the click-through. And we did these questionnaires and focus groups afterward about whether they thought the surprising book sparked a new area of interest for them, and we found some evidence that it did. So we're continuing to develop this and refine the process of how do you build a recommender system that's intention is to inspire curiosity rather than its intention is to give you what you want. And finally, Peak is a system that we've built that builds a sequence of research papers. We call it surprise walks. And it takes what a person knows and what already knows and wants to know, and then constructs a sequence of papers from where they are now to what they want. We ran this in 2 courses. One was a course on HCI, where we had the entire ACM database of papers that had human-centered computing as one of its keywords. And we classified all those and used the keyword representations from the papers to extract the feature vector from the latent space, and looked at the similarity between paper 1 and paper 2 as a cosine similarity of their vectors. From that, we could construct a surprise walk. We ran that through a class, and it was really interesting in the HCI class to see that the students, first of all, they had their own path of papers that they read that wasn't prescribed by the instructor. And then we asked them, which papers did you find most surprising, to see whether it correlated with our surprise metric, and what did you learn from this? And one of the things that we found was that they felt that they really learned a lot more about HCI this way than from what happened in the class, because they had no idea that HCI was such a big field. And this is a 1-semester class. This research papers reading happened in parallel with the prescribed material. So it was interesting to see that that curiosity part worked. Our surprise measure, by the way, didn't work, but we're in the process of refining that. Apparently, if you normalize a paper to a single feature vector, the latent space, you're losing some of the things that make it special and different from the other papers. So we may go back to the PMI. Okay, here's my last slide. We have time for questions, great. I wanted to encourage a discussion, first about computational co-creativity. that computational models of novelty and surprise could be a stimulus for cognitive creativity in ways that we haven't really experienced before. We often thought about the computer as either generating creative artifacts or being inspired by human cognition, but not computers inspiring human cognition. The cognitive models that are associated with creativity, this idea of curiosity, arousal, and the desire to know or learn, is a really interesting cognitive model that would be worth inspiring. Emergence, the ability to see things you could not see before. This is something that through an internal representation inside the computational system, we could present things that intentionally encourage this concept of emergence. Conceptual shift. Analogies are based largely on conceptual shifts. How do we decide where in that space to present the candidates for an analogy? Rather than have the computer perform the analogy, could it be that the computer could present the analogy and then the human could make sense of it? And then serendipity is a very popular term now in information retrieval and recommender systems. How can we use computation and computational models of curiosity to encourage serendipity? Serendipity, it's chance that favors the prepared mind, but not just chance. It should be something that is calculated, that is determined to be on that spectrum of something that's similar but different. And then finally, some interesting questions that arise from this research is, can personalized AI models of surprise encourage this idea of everyday creativity? In that design task, creativity was rewarded in the sense that a designer is considered valuable because a designer is able to come up with ideas or designs that are creative, novel, and interesting to the people who experience those designs. But everyday creativity, everyday curiosity, when we sit down at a search engine, when we decide what we're going to cook for dinner, can we think about these AI models of surprise as actually encouraging that phenomenon, not just that special point when a designer produces a creative design? And then finally, where we're going now, and we don't have anything finished or worth reporting yet, is can these deep learning systems, these models that we build, can they begin to mitigate human bias? There's been a lot of talk about algorithms of oppression, a lot of talk about the bias in the algorithms themselves. But what about the bias in humans? How can we use computational systems to mitigate that part instead of, or in addition to, trying to make sure that our algorithms aren't biased? Just want to acknowledge I have many authors. These ideas have emerged from many conversations, many projects. I wanted to acknowledge some of my co-authors in the papers that led to this presentation and acknowledge funding from NSF for the PEAK project. So I'll leave it back on the discussion slide and open it up for questions. Thank you.